So to finish this chapter now, what we're going to do is we're going to take a look at practical problems involving logs. And I do need you to remember everything we've already covered in terms of logs and indices from the previous part of this chapter, particularly the laws. They are in your tables. You make sure when you're working with logs and indices that you have your tables open on the correct page so you know what formula to use, okay? Because that will make life very easy. The formulas are there to simplify matters. That's why you have those laws, okay? They simplify how we deal with logs and indices, and you must carry those forward. However, when we're moving into practical problems, real life problems, everyday problems, there's one golden rule that I want you to carry forward, and it's very simple. If you wish to cancel a log with any base, you bring in the same base below it, okay? So for example, if I had log to the base 7 of 7 to the power of x equals 10, okay? Straight away, if the base of the log and the base of the index or the exponent match, they'll cancel, leaving you with x equals 10. So in other words, if I had 8 to the power of x equals 15 and somebody said to me, work out the value of x, I want to get rid of the base. So to get rid of the base, I bring in log to the base 8 on both sides. See? Log to the base 8. So that means log to the base 8 cancels with base 8, leaves you with x on the left-hand side, and log to the base 8 of 15 on the right-hand side, which is the answer. Now again, you don't have to go into decimal form if they don't ask you. So if they don't say to you, give your answer correct 3 decimal places, 2 decimal places, whatever, you just give your answer back as log to the base 8 of 15. Okay, and the second thing that's part of that rule is that if you have let's get rid of this now. If you have a base that you want to get, or sorry, if you have a log that you want to get rid of, then you bring in the base on the same side. So in other words, and I'm going to go through some examples here. It might make it easier if I just go through the slides. Going forward, the simplest thing you can do with logs and indices is cancel them as soon as you can. To cancel the base, bring in the log. So to cancel the base, bring in the log. Okay, and let me do an example of that. Solve 7 e to the 7x equals 1. Now what's the problem with this equation? The problem with this equation is that the variable I wish to solve is written as a power. Okay, it's in the index of base e. So therefore, if my variable that I want to solve is in the index of base e, then I have to get rid of base e in order to free up the 7x, so to speak. Okay, so the first thing I'm going to do here, follow your normal rules of algebra. The first thing I'm going to do is I'm going to divide both sides by 7. That gives me access to the base e. So that's equals 1 over 7. Now, to get rid of a base e, we're going to bring in log to the base e. Okay, so if I want to get rid of a base, I bring in log with the same base. So I'm going to bring in on this side log to the base e, and exactly the same thing over here, log to the base e. And now I notice that the base of the log and the base of the exponent are exactly the same. And if the base of the log and the base of the exponent match, they cancel, leaving you with 7x is equal to log to the base e of 1 over 7. Now I hope you remember back in one of the previous classes, log to the base e has a shorthand way that we can write it down. It's known as 7x equals natural log of 1 over 7. Log to the base e is also the natural log. You can use either form, but they are interchangeable, so please remember that. And the final thing I want to do then, obviously, to get x on its own, is to divide both sides by 7. And when I do that, I get x equals the natural log of 1 over 7 divided by 7. Now, if you're not asked for decimal answers, don't bother giving them a decimal answer. Leave it as that. Just get your formula, manipulate your formula, isolate your variable, and leave the other mess on the other side exactly as it is. Okay? Now, if you were asked to get it into decimal form, obviously you turn on your fraction, you press your natural log button, and it's a dedicated natural log button in your calculator. You put on your 1 over 7 after it, and underneath that then you put in 7, and you get an answer of minus 0.278, correct to 3 decimal places. Okay, that's if you're asked to do that. So, if you want to cancel a base, bring in the log. Now, say the opposite. If you want to cancel a log, bring in the base. Okay, so let's take a look at the next question. Daisy. To cancel the log on its base, bring in the same base on both sides. So if you want to cancel a log, bring in the base. Cancel a base, bring in the log. And that's all you've got to remember going forward. And I'm going to do 2 examples of real life situations in a moment that'll give you an idea how that works in practice. So here's another question. Solve log to the base e of the third root of e, which is equal to x. Now you're probably saying to yourself, hold on a sec, is that not solved? X is already isolated on the right hand side. Yes, but can I tidy up the left hand side? Can I actually work out what the value of log to the base e of the third root of e is? And the answer is only if you remember your index rules. And your index rules tell you, first of all, that any root is a fractional power, okay? And the third root is a fractional power of a third. So let me just start to tidy this up a little bit. The left-hand side becomes log to the base e of e to the third. See that? Which is equal to x. And again, notice the base of the exponent and the base of the log match. Line, line. What do I end up with? 1 over 3 equals x. So we've actually managed to tidy up the left-hand side and reveal the true value of x as something that we know is 0.33333 recurring. Okay, so again, remember going forward, if you want to cancel a base, bring in the log with the same base. If you want to cancel a log, bring in the same base on both sides. So let me do some examples on that now, going forward. Let's take this question here, page 190, question 3. The radioactive substance iodine 131 is used in medicine to measure liver and heart activity and in the treatment of certain cancers. It has a half-life of 8 days, i.e. the quantity of iodine 131 decays by a factor of 2 in 8 days. A hospital purchases 30 grams of the substance and in 8 days 15 grams remain. Okay, that's what I mean by a half-life. Half-life just means how long it takes for a certain radioactive species to decay to half its original value. Okay, so 30 goes to 15 in 8 days. A decay model using the exponential formula Q equals A, E, B to the T, where A and B are constants and T is measured in days and Q is the quantity. They want you to find the value of each of the constants A and B. Now, if I want to find A and B, well then Q and T must be given, okay? And there's 2 things we have to realize from this question, and this is where we begin to pull out the information. First of all, T is time, okay? And the most important time for any particular experiment or any real life situation is the start. What did the hospital purchase? A hospital purchases 30 grams. When? On day 1. Or I should say T equals 0. At the very start we purchased 30 grams. So when T is equal to 0, what does that mean? The quantity of radioactivity is equal to 30 grams. So there's the first thing I pull out of that paragraph. The hospital purchases 30 grams at the beginning of this particular situation. And the beginning of any situation is T equal to 0. In 8 days, so when T equals 8, what does that mean? Q drops down to 15 grams. So there it is. In 8 days, 15 grams remain. So from that paragraph, you've got 2 equations. T is equal to 0, Q is equal to 30. When T is equal to 8, Q is equal to 15. Now, they have to be used together with Q equals A e to the bt in order to reveal the values of A and B. So let's do the first one. When T is equal to 0, okay, so let's come down here. Q is equal to 30. So take these 2 together into this equation. Q is 30. 30 equals A e to the B times 0, because when T is 0, Q is 30. At the start, we bought 30 grams. So the quantity is 30 at the beginning. See that? B times 0 is 0. Any base to the power of 0 is 1. And 1 times A is A. So straight away, I've discovered A. How do I discover B? Well, first of all, I rewrite the equation now with the newly discovered value of A in its place, e to the bt. So I'm going to use equation 2. When T is equal to 8, so 8 days later, the quantity drops to 15. So Q is 15 when T is 8. Put them in. 15 equals 30 e to the b times 8. Okay, because that's what they told me over here. In 8 days, 15 grams remain. Now, let's divide. I want to get the value of B, and B is stuck in an index. If B is part of your index, you're going to be using logs to clear the base of that index. So if you want to get rid of a base, you bring in a log. Okay, there's the rule. So let's divide across first of all by 30. 15 over 30 is equal to e to the 8b. Now, to reach the 8b, we've got to get rid of the e. If I want to get rid of base e, I bring in log to the base e on both sides. So log to the base e of 15 over 30 is equal to log to the base e of e to the 8b. And when the base of the log matches the base of the exponent, that cancels with that to leave you with log to the base e of 15 over 30 is equal to 8 times b. So therefore b would be log to the base e of 15 over 30 divided by 8. And again, if you want to put that down in decimal form, which might make a little bit more sense in a real life situation here because you could be using it later on, and you certainly don't want to use it as that mess there. You put on your fraction. Now, log to the base e has a dedicated button. Log to the base e is the natural log. So ln of a half, because 15 over 30 is a half. So turn on your fraction there. 1 over 2. Close your brackets. And below that then 8. And the answer comes out for b as minus 0.087. 3 decimal places. So that's b. So there's b and there's a. So now what do I have? Now I have the formula completed. So I can go back to this formula here and I can write it down as q equals 30e to the minus 0.087t. So in other words, once I find the values of a and b, I fill them into the formula and I now know what formula I'm dealing with. So that's part 1 finished. For part 2 and part 3, I'm going to use that formula. Okay, so let me just take a moment here just to get rid of this stuff here because I don't need this anymore. That's helped me to find a and b. So that's done. And what they'll ask you to do now, once you've discovered what the formula is they'll simply ask you to use it to show that you know how to use this formula. They're going to give you certain questions about the formula that they will ask you to use. So let's take a look at that. Part 2. What quantity of the substance will remain after 20 days? Now, what are they giving me? They're giving me time. What are they asking me? They're asking me for quantity. Okay, so what quantity? So Q will stay Q. Of the substance will remain after 20 days. So T will become 20. So you take these two into the new formula and you'll get Q equals 30 E to the minus 0.087 times T, which is 20. And that is something that you can do in your calculator. So 30, E, by the way, the function E is above the natural log. It's the second function of the natural log because they're inverse functions. So it's the second function of the natural log. So shift natural log to get your E minus 0.087 times 20. And that comes out as 5.265. So that's the quantity in grams. That's the quantity after 20 days. Okay. Part 3. Find the time taken for the substance to decay to 1.49. What are they giving me here? They're telling me Q is 1.49 grams and they're asking me to work out the value of T. So again, I bring these two back to this formula and I get 1.49, that's Q, equals 30 times E to the minus 0.087t. So now my job is to work out the value of the variable t. So the first thing I do is I divide both sides by 30. That's 1.49 divided by 30 equals e to the minus 0.087t. Okay, now how do I get to t, which is in the index of a base? The answer is clear the base. But how do I clear a base? You clear a base by bringing in log with the same base. So in other words, if I want to clear base e, I'm going to bring in log to the base e, better known as the natural log. So I'm going to get natural log of both sides. Let's just bring that up here. The natural log of 1.49 over 30 is equal to the natural log of e to the minus 0.087t. Look what happens. Natural logs and exponents, whenever they meet, they cancel. So you get the natural log of 1.49 over 30 equals minus 0.087t. ln of 1.49 over 30 is equal to minus 0.087t. Now you'll notice I haven't done any calculations yet. I am manipulating the formula before I go to the decimals if needs be. And the last thing to do to get t on its own is to divide across by minus 0.087 there and minus 0.087 here, and that cancels with that to give t equals, and just plug that mess into your calculator, turn on your fraction, turn on your natural log, turn on your fraction again, 1.49 over 30 on top, and then on the bottom minus 0.087, and the answer there comes out to be 34.51. So therefore it takes 34.5 days in order to have the 30 grams of radioactive material to drop to 1.49 grams of radioactive material. So you can see what's happening. If a question involves a base E, the natural log is going to be used. Okay. If a question involves any log with a given base, then the question is going to involve bringing in that same base on both sides. Okay, so let's just do one more example. And the next one is on page 191, and it's in question 7. Normally, human blood has a hydrogen ion concentration of 1.3 by 10 to the minus 8 moles per litre. Now, that's for us chemists. Don't worry about that. If you're not doing chemistry, don't worry about moles per litre. Just think mathematics. pH is given by the formula. Okay, so here we go. We've got a formula. pH equals minus log to the base 10 of the hydrogen ion concentration, H+. Okay, now, log to the base 10. Okay, that's the common log. Remember that? So therefore, you don't really have to write in the base 10 at all. pH equals minus log of H+, if you wanted to. Okay, now I would suggest only do that when you're familiar with it. Okay, but just to understand that they would be exactly the same thing. We spoke about that before. So let's stick with the one that we already have, the one that we're given in the question. So what are we told? Determine the normal pH of human blood. So what I need to do now, it tells me H+ in square brackets is the hydrogen ion concentration. Well, they gave me the normal hydrogen ion concentration up here. So what I've got to do is stick that value in here. So pH equals minus log to the base 10 of 1.3 by 10 to the minus 8. So again on your calculator, minus log to the base 10, which is minus log. You'll notice there's no log to the base 10, it's just log. It's beside the natural log. So minus log of 1.3 by 10 to the power of minus 8. I close the brackets, and the answer comes out as the pH of human blood normally is 7.89, just to round it off to 2 decimal places. Okay, so that's the pH normally of human blood. Part 2. A condition known as acidosis sets in when the pH of a person's blood drops below 7.45. Acidosis can result in death if the pH reaches 7. What would the hydrogen ion concentration of a person's blood be at pH value of 7? Now, what are they giving me? They're giving me the pH value. So again, I go back to the formula, the original formula. pH equals minus log to the base 10 of the hydrogen ion concentration. Question says, what is the hydrogen ion concentration? So we have to work out the value of H+. But they give me a pH value of 7. So 7 equals minus log to the base 10 of my H+ that I'm looking for. Now, first things first. Let's start to work in towards this H+. Let's multiply both sides by minus 1. Minus 7 equals log to the base 10 of the hydrogen ion concentration. And the last thing to do to get the hydrogen ion concentration on its own on the right hand side is to get rid of this log to the base 10. And the only way that I can get rid of log to the base 10 is by bringing in base 10 on both sides. Okay, so in other words, the left hand side and the right hand side become powers of the base 10. And that means that if you have base 10 and log to the base 10 meeting, working together, they'll cancel each other. And what does that give you? That gives you 10 to the minus 7 is the normal hydrogen ion concentration of human blood. 10 to the minus 7 is the hydrogen ion concentration of somebody who has acidosis if their pH levels drop to 7. So there's just 2 examples, one on how to get rid of a base, and 2 how to get rid of a log. And those are rules that you will carry forward from here right the way through the rest of this course, because logs and indices are going to come up all over the place from now on. And the key thing to remember is when they appear, do everything in your power to get rid of them so that you can work simply with the algebraic terms. So just to make sure that you understand how that works, I'm going to ask you now to turn to your page 190 in your textbooks and to answer questions 1, 2, 4 and 6. And that finishes this chapter. Okay, so we will have a live class on Monday. We'll go over logs and indices and the real life situations on Monday, and then next Thursday we will have a test on this chapter. Very, very simple test. There's not much you can ask about logs and indices on their own because they're kind of scattered throughout the rest of the chapters, but we will have a short test next Thursday based on this chapter. In the meantime, when you're working on these questions, if you need any help with them, just ask.